Particles from gravity. I'd like to read you an article I wrote about it, rather than following precisely the formal article, which you can read. This article is entitled "Why Particles Might Need Spin." We know particles have spin because the literature and something happens in experiments to particles subject to magnetic fields that is explained abstractly in quantum theory. But we are talking about something that actually spins like a top or a whirlwind. Why would such a proposed particle need spin, actually rotate? It might start with Mach again, whose principle was an early inspiration to Einstein for general relativity. Recall, Mach saw himself in a stationary reference frame and imagined the universe spinning around him, rather than spinning himself and watching his arms move outward due to centrifugal force, in quotes. He thought there must be some connection between himself and the universe at large. It has been suggested in previous posts at this site that there might indeed be such a connection. If gravity is fundamentally repulsive, seated in the large-scale cosmic voids, possibly housing dark energy, surrounded by galactic supercluster shells, the gravitational/dark energy field would point from the center of the essentially spherical voids to the visible matter shells. This is an active field, causing the void and surrounding supercluster shell to expand under acceleration. Each field line, so to speak, is pointing and contacting a corresponding particle of matter in the visible matter shell. Now, if this connecting gravitational field line is thought to be a fine silk spider thread, one for each subatomic particle in Mach's body, when he spins around, all those individual threads might tend to twist them like someone twisting a wet rag to get the water out. Both Mach and each particle within him might feel the effect. The incoming field might tend to concentrate. The faster he spins, the greater the effect. In this way, mass might be non-local. Each particle making up Mach would have to be spinning at high rates to achieve a strong concentration of a field, strong force, for instance, that comprises quarks and holds its protons and nucleons together. It is at least conceivable, then, for the strong force to be derived from weak gravity. Next here is an equation for the strong force, which I will not talk about here. You can read it in the formal paper. This expression represents the predicted force containing quark integrity and the strong force. It was derived with special relativity and Newtonian gravity implied. In the relativity portion, the velocity of the spinning field was made to approach light speed. The equation was theoretically confirmed by its use in an expression that derived the unit charge, electron charge. Considering special relativity in the conventional manner, where a particle is made to approach light speed in a linear accelerator, for instance, the mass of the particle is commonly said to increase. This mass increase should increase the gravitational field of the particle. Thus, the spinning and linear motions might yield similar effects, in that a spinning entity has part of itself moving at a tangential velocity near light speed. Now, to compare the proposed non-local source of mass and the conventional local source. Non-local mass and strong force, seated in cosmic voids but pointing at and contacting the particle. Spinning directly might cause higher field by concentrating weak field lines. Common low-intensity gravitational field, the sole participant, proposed. Local mass, seated in the particle, said to derive from the Higgs field, conventional quantum theory and experiment, gravity not included. So non-local particles might need spin to activate special relativistic effects in the proposed in order to boost the marginal effects of a repulsive form of Newtonian gravity. This repulsive form of gravity has been discussed in previous posts at this site. Now, this is the last article in a series of articles that I wrote about the paper. I would say the last one first, just in case there's not enough time at the conference. I'll stop now and read another one at this time of the conference. I'm going to go out of sequence here and read just part of another article. It's entitled, Could Particles Be Gravitational Sinks Rather than Sources? Okay. This hypothesis is theoretically testable in that the field of newly created particles, for example, a particle accelerator, should move out from the supposed sources at finite speed, while the gravitational field of the sinks would not. The field of the sink already exists in proximity to the particle to be, originating in large-scale space since the Big Bang, and would immediately be connected to large-scale space on creation in the machine. The question of the particle infinities problem might also be resolved if particles are gravitational sinks. Regardless of how close particles might approach or how close one approaches a particle, the field would not approach infinity, as is the case in the current thought. Renormalization would not be required in small-scale calculations, and that the gravitational source could be external to the particle, everywhere except at the particle proper. Particle proper might be roughly described as the field lines from space at large intersecting at a point and canceling, such that the point is effectively an absence rather than a presence. Particles might be inherently non-local, in possible accord with Bell's theorem. The two-slit experiment, where a single particle is seen to interfere with itself, might also be less of a puzzle. The particle might be everywhere except where it is apparent in the detection medium. The observer might be noting where the particle is not. The embarrassing calculation of the infinite mass of the quantum vacuum might also be resolved if particles are sinks rather than sources. This is the end of this article. And this next article is actually the first in the series, and it's rather short, and I'll read it in its entirety. It's called Big Bang to Big Sponge. When a catalyzed liquid is expanding to an open-cell sponge, it appears as a miniature piece of the dynamic large-scale structure of the universe. The voids of the material are basically spherical. As the voids expand, they press the material aspect into sheets and filaments, simultaneously displaying repulsive and attractive effects. The repulsive effects are in the voids, and the attractive effects appear to be at the material. The material is compressed by almost adjacent expanding voids. This sponge example might mirror what is occurring in the large-scale structure of the universe. The expanding gas bubbles of the sponge might represent the cosmological constant and/or the quantum vacuum energy or other agent, see below, possibly causing accelerated universal expansion. And the sheets and filaments of the sponge material might represent galactic superclusters, apparently being compressed into the observed astronomical sheets and filaments. The expansion of space does not occur, as is so often illustrated, where all dots painted on the surface of an inflating balloon move away from one another. You see this a lot in books. Such clusters if this was the case, clusters of galaxies, and all below this level, would not remain stable. Such clusters are fundamental astronomical units. The expansion of space, according to the Hubble law, occurs above this level. In order to properly use the raisins in the loaf cake analogy, the raisins must represent clusters of galaxies. It is above this level that the universal expansion is apparent, and at and below this level where attractive gravity is apparent. Note the complementarity of the loaf cake and sponge analogies now, but with the addition of a possible reason gravity only appears attractive below superclusters. The yeast is primarily in the loaf and only marginally in the raisins, thus the raisins are stabilized. Again, this suggests the possibility of a repulsive gravity in place of the active expanding agent, in that the viewpoint becomes key. From the viewpoint below superclusters, gravity might only appear attractive. At the large-scale level of large space voids surrounded by galactic superclusters, where expansion is most apparent, gravity might be fundamentally repulsive. Now, we're talking about this type of repulsive gravity in place of, or another candidate for the quantum vacuum or the cosmological constant. This ends this article. There are several other articles in this sequence, but I think it might be better if you read them yourself, like I am, off my LinkedIn site, and because there's quite a bit of repetition. So we'll close right here. Okay.